We present Greedy-DAgger, a rollout-efficient on-policy imitation learning approach. Imitation learning is a technique for transferring knowledge from an expert to a student policy. By leveraging a readily consultable but computationally expensive expert, our approach aims to reduce the overall rollouts required to train a policy. For this work, a model predictive path integral controller provides expert samples and a two-layer neural network is used by the student. We demonstrate Greedy-DAgger in a quadcopter waypoint environment. The student must control a quadcopter to navigate from a random initial pose to a random goal pose, shown here as the blue dot. It then must maintain a stable hover at the goal pose. First, the student performs an environment rollout by following its current policy. For each state the student visits, the expert generates a control action. The error between the student and the expert's control action is calculated and stored with the associated state. A greedy algorithm then selects states with a high control error but far Euclidean distance from already selected states. These states are visualized here as red dots along the student's trajectory. Using GPU-accelerated parallel processing, the MPPI expert simulates future trajectories from all selected states, displayed here as red lines branching from the student trajectory. These samples are added to an expert action dataset, which is used with supervised learning to train a new student policy. The new policy is then evaluated in simulation to assess if the student has achieved expert level performance. This process is then repeated if the student has not reached the expert. Greedy-DAgger can train a policy for a cart pull swing up task within 8 rollouts, a 6-fold improvement over the conventional Dagger approach. For the previously seen quadcopter waypoint task, the student achieves expert performance within 4 rollouts, a 5-fold improvement over conventional Dagger. After 30 seconds of training in a multiple waypoint quadcopter environment, we deployed the learned policy to a crazy fly quadcopter to evaluate its performance and verify the simulated quadcopter environment. For this experiment, 10 waypoints were randomly placed within a 1 meter cube. The real-world crazy fly student manages to successfully navigate between waypoints, however it is slower than its simulated counterpart and a simulated expert. This response could be due to the zero-shot transfer resulting in a model mismatch between the simulated and real-world systems. This experiment, however, does verify the simulation environment. Future work could look to add model parameter identification, as well as introduce safety layers, such that student rollouts could be conducted using real-world samples.